Hi everyone, welcome to the session on number properties. This is an additional session on factors and prime numbers. Factors, prime numbers, divisibility is one of the important topic in the number properties from where you can expect some good questions. One of the concept which I would like to introduce to you is counting factors and prime numbers. So on this topic, GMAT may ask you to count factors or prime numbers in the following way. You may expect a question, how many different prime factors are there of a number, or how many total prime factors are there of this number. This is also called the length of the number. So the GMAT may ask you what is the length of the number, or how many total factors are there of the number. So these three kind of questions can come in GMAT. So let's take an example of 600. Let's factorize 600. So I factor it by 2. So I get 300. Then I divide by 2 again. I get 150. I divide by 2 again. I get 75. I divide by 3. I get 25. Then I divide by 5. I get a 5. So 600 can be written as 2 cube into 3 into 5 square. So this we have factorized 600. Now let's try to answer these questions. So how many different prime factors are there in the number 600? The answer to this is 2, 3, 5. These are the different kind of distinct prime factors that 600 is having. So the answer to this question is 3. Now let's see how many total prime factors are there, or what is the length of 600. So this is nothing but that how many factors are there in the prime box of 600. So we have 2, 2, 2, 3, 5, 5. So answer to this question is 6. Or simply, if we do the addition of exponents of the prime factorization. So 600 is equals to 2 into 3 plus 3 raised to power 1 into 5 square. So we add these exponents to get how many factors are there. That is 3 plus 1 plus 2, which is equals to 6. Now if we have to calculate that how many total factors are there. Although 600 is a big number, let's use the small and large technique as I told earlier. So first, let's write 1 here in small. So 600 divided by 1 is 600. Then we take the next number 2. 600 divided by 2 is 300. Then we take the next number 3. 600 divided by 3 is 200. Then we take 4. 600 divided by 4 is 150. Then we take 5. 600 divided by 5 is 120. Then we take 6. 600 divided by 6 is 100. Then we take 7. But 7 is not divisible by 600. Then we take 8. 600 divided by 8 is 75. Then we take 9. 9 is not divisible. Then we take 10. 600 divided by 10 is 60. Then we take 12. 600 divided by 12 is 50. Then 13, 14 are not divisible. Then we take 15. 600 divided by 15 is 40. Then the next number which is divisible by is 20. 600 divided by 20 is 30. Then 21, 22 and 23 we cannot divide 600. Then we take 24. Then 24 gives us the factor pair of 25. So if we count, there are 24 total factors of 600. So what are those 24 factors? 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 600, 300, 200, 150, 120, 100, 75, 60, 50, 40, 30 and 25. To summarize, how many different factors are there of 600? 3, 2, 3, 5. How many total prime factors are there? 6. And how many total factors are there? 24. However, this number 24, it took a lot of time to do the factor pairs of 600. And we studied that factor pairs we'll use only for the numbers up till 100. So now let's see another method. For bigger numbers, the first step to find out the factor pair is to do the prime factorization of a number. Prime factorization of a number. For example, there is a number x and its prime factorization says x into a, y into b, z into c, into so on, where x, y, z are the prime factors, a, b and c are the exponents of those prime factors. If we see 600 is equals to 2 raised to power 3 into 3 raised to power 1 into 5 raised to power 2. So the number of total factors of any given number is nothing but a plus 1 into b plus 1 into c plus 1 and so on. So in case of 600, the total factors is equals to 3 plus 1 into 1 plus 1 into 2 plus 1, which is nothing but 4 into 2 into 3, which is 24, which is the same number as we see here. Okay, so this is other way to calculate the total number of factors from the prime factors. So to summarize, total number of factors of x, where x is equals to x raised to power a, y raised to power b, z raised to power c and so on, where x, y, z are distinct prime factors and a, b, c are exponents of those prime factors. The total number of factors is a plus 1 into b plus 1 into c plus 1 and so on. So let's see another topic, perfect squares. GMAT also occasionally tests properties of perfect squares and rarely on perfect cubes as well. So there are two special properties of perfect squares which we must remember. That is, all perfect squares have odd number of factors and the prime factorization of a perfect square contains only even powers of prime. So let's consider an example of 36. Let's factorize 36. So 36 divided by 2 is 18. 18 divided by 2 is 9. Then there is a 3 and a 3. So 36 we can write as 2 square into 3 square. Every time whatever is a perfect square, the prime factorization of a perfect square contains only even powers of prime. So prime factors are 2 and 3. It has only even powers there. So now let's try to do the factor pairs of 36. So I write here small, large, just to see what are the factor pairs of 36. First 1, 36. Then let's take the another number 2. 36 divided by 2 is 18. Then we take 3. 36 divided by 3 is 12. Then we take 4. 36 divided by 4 is 9. Then 36 is not divisible by 5. Then we take 6. 36 divided by 6 is 6. So if you see, when we divide 36 by 6, since it's a perfect square, the last number comes same. That's why we say that all perfect square have odd number of factors. So what are the factors of 36? 1, 2, 3, 4, 6, 36, 18, 12 and 9. So how many factors are there? 9 factors of 36 are there, which is a odd number. Now let's see a question that by using property 2, how does GMAT may ask questions. If a cube is divisible by 240, what is the least possible value of integer a? 5 options are given. So definitely it's a problem solving question. So now let's see what is given in the question. It is given that a cube is divisible by 240, or in other words it is given that a cube is a multiple of 240. Okay, so let's break 240 first. So what is 240? 240 is 2 into 2 into 2 into 2 into 3 into 5. So this is the prime factorization of 240. So the prime box of 240 if we make, we get 2, 2, 2, 2, 3, 5. Since a cube is divisible by 240, let's see the prime box of A cube. So the prime box of A cube will have the numbers 2, 2, 2, 2, 3, 5 and some other factors as well. It will have the factors of 240 and it will also have other factors. Another way to look at this is the prime box of A cube will have the factors of A appearing in the sets of 3 as well. So for example, if we have to draw the prime box of A cube, how it will look like? The prime box of A cube will look like having 3 prime boxes of A each. So it will be having factors 2, 2, 2, 2, 3, 5, and here some of the factors must be repeating themselves so that it becomes the prime box of A cube. Even though 240 does not contain additional instances of 2, 3 and 5, the factors must be repeated for every A. All the A's must be identical. We see here that there is a complete set of 3 2's in the prime box of A cube. However, there is a fourth 2. That additional factor of 2 must be from A as well. Here also the 2 must be there and here also 2 must be there. Similarly, to complete the prime box of A cube, there must be 3 and 3 here, 5 and 5 here. Then only A cube will be considered as a perfect cube. There might be some other factors also of A cube into this box. Thus, each A has 2, 2, 3 and 5 at least in its prime box. So, the least possible value of A is equals to 2 into 2 into 3 into 5, which is nothing but 60. So, the answer to this question is 60. To summarize, 240 is equals to 2 into 2 into 2 into 2 into 3 into 5. It contains 4 2's, 1 3 and 1 5. So what will be the potential prime box of A cube? Potential prime box of A cube will have 3 prime boxes of A each. Since we have 4 2's, the 3 2's are divided into A's. The fourth 2 is written here. The 3 is written here. The 5 is written here. So the 2 will come here. 3 will come here, 5 will come here. So the at least value of A will be nothing but 2 into 2 into 3 into 5 is equals to 60. So the answer to this question is 60. There is another important topic which is tested in divisibility is the factorials and divisibility. Since n factorial is the product of all the integers from 1 to n factorial must be divisible by all integers from 1 to n. So for example, 5 factorial is equals to 5 into 4 into 3 into 2 into 1. So 5 factorial must be divisible by 5, must be divisible by 4, must be divisible by 3 and must be divisible by 2. This is the first property of factorials. The second property is this fact works in sync with addition subtraction properties of multiples. For example, 5 factorial plus 4 must be divisible by 4. Since 5 factorial is divisible by 4, if we add another multiple of 4 into it, so 5 factorial plus 4 must also be divisible by 4 by the addition and subtraction property of multiples as we studied in the factors chapter. Okay, so these are the two properties. Now let's see how the question can come. Which of the following numbers is not a prime? Which of the following number is not a prime? Let us see the numbers. So in the first choice, in the choice A, the number given is 6 factorial minus 1. We know that 6 factorial is not prime because it is divisible by 6, 5, 4, 3 and 2. If we see 6 factorial minus 1, it may be a prime number, it may not be a prime number. we can only find out if we calculate it. But in GMAT, we don't have that much time to do such big calculations. Correct? So now let's see option C as well. It says 6 factorial plus 41. Okay. So 6 factorial definitely is not a prime. And if we see 41, since it's a prime number and it does not have any common factor with 6 factorial, so 6 factorial plus 41 may be a prime number, may not be a prime number, we don't know. If we see option D, 7 factorial minus 1, it may be a prime number or it may not be a prime number because 1 and 7 factorial does not have common factors. If we see E, 7 factorial plus 11. 7 factorial is definitely not a prime. 7 factorial plus 11 may be a prime number, may not be a prime number. So until we calculate, we will not know. But why do we calculate? Let's see option B now. Option B says 6 factorial plus 21. 6 factorial is definitely not a prime. 21 is also definitely not a prime. By adding two not prime numbers, we may get a prime number or we may not get a prime number. So how to solve it? So the factors of 21 are nothing but 3 and 7 apart from 1 and 21. Correct? So 6 factorial is divisible by 3 as we studied above, and 21 is also divisible by 3. It has a common divisor, means if 6 factorial is divisible by 3, 21 is divisible by 3, then definitely 6 factorial plus 21 will be divisible by 3. So definitely 6 factorial plus 21 is not a prime number. It can be divided by 3 very easily. Okay, so these are the kind of questions which may be tested on factorials and divisibility. So prime numbers is an important topic. If it gets combined with factors, multiples and divisibility rules, it becomes an important topic of GMAT, especially in harder problem solving questions and some of the data sufficiency questions as well. So to summarize, 6 factorial plus 21 is not a prime number since it is both divisible by 3. Thank you so much. I'll cover all the other number properties sessions in the next videos. Bye bye.